Okay. Welcome to the second Boost Geometry talk today. I'm Adam, I work at MySQL, and I'd like to talk about spatial reference systems and how to transform between them in C++ with Boost Geometry. So when we are dealing with coordinates, we have to know the context for them, how to interpret them. They may be on the surface of a spheroid or on the sphere. We have to know the parameters of the spheroid, or maybe these coordinates are on a map, so they are Cartesian coordinates. In this case, we have to know how this map was created to interpret them properly. The most simple thing that could go wrong is missing of units. For instance, we could have coordinate system using meters or feet. Typically, right, and so this is what a space reference system defines. So basically, it defines the context of coordinates we're using. And typically, the space reference system is referred to with a number. And there are some multinational organizations defining such numbers. The most known one is the EPSG, which is now a part of International Association of Oil and Gas Producers. But there are also others like ESRI, and there are also numbers of space reference systems for objects in space, like Moon or other planets. And this is the last one mentioned on the slide. Here you can find various coordinate system defined. So the first two ones are defined by resources for APSG reference systems, and the third one contains also ESRI and the astronomical ones. And when you go to one of these sites, you will have you'll see basically two definitions. This is the first one. So this is the WKT format, so well-known text as defined by the OpenGeo consortium. So this is basically the standard one. And this particular one defines the standard WGS 84 coordinate system, so longitude and latitude on spheroid in degrees. So basically, the data you are seeing, for instance, in some GPS tool returns the coordinates in this system. And this is the same coordinate system defined in a Proch4 string. So Proch4 is a well-known library written in C with wrappers to many languages. And this is how projections are defined in this library. So during this talk, I'll be talking about Proch4, or actually I'll be talking about Boost Geometry, but with relation to Proch4 because this is the state-of-the-art library. The most recent version is 5.2, and here are the addresses. And Boost Geometry implementation is based on Proch4. It was started some time ago by Baron Gehrels when Proch4 was in version 4.03 or something like that, and I finished it. And most of the things you'll see are already released in Boost 169, and some of them will be in 170. This presentation will be example driven. So this is my data. I took the data from Eurostat. So basically boundaries of countries of the world represented as polylines. So here is the address at the top, and you have to navigate to find the file. And I'm using, as you can see at the end of the file, I'm using a shapefile, and these are coordinates in WGS84, which is EPSG 4326. This is how it looks like. What I would like to do basically is I would like to create 3 maps. So these are geographic coordinates. I'll be creating 3 maps, one of Poland, one of Belgium, and one of New Jersey. And I'll say why New Jersey later. So these are raw geographic coordinates of boundaries of Poland and neighboring countries. So I know if you know what's the shape of Poland, but this is distorted. And what I'd like to do is to create a map representing the reality more closely, more accurately. And for this purpose, this SRID is used, so EPSG 2180. It's used for maps of scales to 1 to 10,000, I think, because for closer scales you have to use another one. And the SRID is called, there are two other names behind the EPSG code, and the first one is the European one, and the last one is Polish name for this for this projection. So how it's defined? This is the definition in WKT. As you can see, it's on a different spheroid than WGS84. It's fourth line. In degrees, and these coordinates are projected using transverse Mercator projection, which is something like this. If we project the whole world, and this is how it's done in C. C++ because I'm using vector in row Proch 4. So we are creating 2 projections. PJ init plus takes Proch 4 string, so this different kind of defining a projection than WKT I shown at the beginning. Then I have some array of coordinates, which here is a vector, and then I'm calling PJ transform function passing the coordinates. And I have to free the projections because essentially these are pointers. And now how it looks like in Boost before that, in Boost geometry we can express the abstractions directly in the code. So here I'm expressing geographic points, line strings, and creating multi-line strings, and doing the same for Cartesian, because my input will be geographic and the output will be Cartesian. And here is how it looks like in Boost geometry. This is one possibility. I will later show other ones, but this is the basic one. It's the closest to Proch 4. So we are just passing the same Proch 4 strings. The only difference is that in C++, the creation and destruction is handled automatically, and I'm passing input multi-line string, which is geographic, and as output multi-line string, which is Cartesian. And I get the transformation you've seen before. Right. So another example, the same story. Belgium, raw geographic coordinates, and this is how it should look like. And again, standard standard space reference system for Belgium, number EPSG 31370. So this is the definition from yet another spheroid using degrees and using a different kind of projection. So before there was transverse Mercator, and here we have Lambert conic. So this is the way you already seen how to create the transformation in boost geometry. So the first one, the first projection is from which we are transforming, and the second one is projection to which we are transforming, right? So we are transforming from WGS84 to this map projection with high number of parameters. So this is the first possibility. So obviously the strings has to be parsed, parameters extracted, which takes time. But there is a better way, which looks like this. It's very similar. The names of parameters are the same. However, it's the numbers are expressed directly in the code, which means that they doesn't have to be parsed. Obviously, this should be faster. Here you can see the two WGS84 parameter, which are parameters used in conversion between ellipsoids, and I'm passing C++11 initializer list as range, but you can pass any range you like. But there is yet another way, because here parameters are added to the list in runtime, but you can create a list in compile time. It should be even faster. So when you pass a type, well, two types representing projections into transformation as template parameters, then the projection exactly knows what you will pass in the constructor, and it expects exactly what you defined in the type. So this should be even faster. And I will show benchmark that it is really. But there is another way. So if you include this optional header, which contains a lot of EPSG codes, there is 7,000 or something like that, which increases the compilation time greatly. But if you enable it, if you include it, then you can simply pass the numbers. So the upper one is the runtime version, and the lower one is compile time version, which below the surface use the interfaces I shown on previous slides. And here are the benchmarks for the Belgium set. It contains 7,000 points roughly. So in the table above there are creation times, and in the table below there are transformation times. So 5,000 creations of transformation object, and adequate Proch 4 projections, and below the transformation of the coordinates. And as you can see, right, and in the first column you have Proch 4. In the second column there is boost geometry using Proch 4 strings. The third one is boost geometry using the runtime parameters directly expressed in the code, and the last one is static parameters. So as I said, the creation is faster with boost geometry in all cases. We're parsing the strings differently too. So this is why This is why we're faster than even in case of Proc4 strings. And we are slightly faster in case of transformation itself. Because internally, we are doing things differently too. And this is the last example, New Jersey. I'm showing New Jersey because, as you will see, it uses North American datum 27, which requires to use grid shifting. So instead of transformation between ellipsoid using a set of numbers or an array, we are transforming between ellipsoid using grids. So lookout table, basically. And this is the first SRID I found on the in the US, because it basically is used by the US and Canada areas, which isn't yet deprecated and was on the near the sea, so we could see the boundaries. So this is the definition in WKT. The interesting thing here is that previous projections used meters, but here we have feet. It's the fifth line from the bottom. So this way you've seen already, right? From WGS84 to this another kind of projection, but if you do this in boost geometry, the grids won't be used. So in boost geometry, unlike in Proc4, you have to explicitly define where the grid storage will be, where the grid will be stored, and you have to initialize them explicitly and pass. It's because Proc4 does it under the hood, looks for grids which are basically huge text files. Oh, maybe not text, probably it depends. But huge files somewhere on a disk. Proc4 looks in some standard directories, like the directory of a program or a user directory. But this is not acceptable, I think. So here you have to do it manually. And here's the, let's say, one thread example. So I'm creating grid storage. I'm passing stream policy and grids. So the first parameter tells how to access the file. So it defines what kind of stream and how to open it, because you can have a grid in a string already loaded, whatever you like. So this default one searches for a file in the program directory and uses if stream. And the second parameter, grids, is the way to tell the library to use single threading. And then we are creating the transformation and initializing grids, which then they are passed to forward methods. So the only difference, if you want multi-threading, the only difference is that instead of SRS grids, you are passing, you have to pass shared grids. And currently, shared grids use boost thread. So you have to link this library if you want to use them. I think in the future it will be possible to use STD threads. However, as far as I remember, internally I used unique lock and shared lock, and I'm not sure when they were added to the standard. It's possible that in C++ 17, and this is why I use boost thread. But I would have to check it. And so the same story, storage, which may be defined anywhere, and basically should be shared between all transformations, because it's more or less global thing, as you don't want to load the same file multiple times. But this way you have control on when it will be created, when it will be destroyed. You can destroy it or keep it, unlike in Proj 4, I think. Then transformation, initialization of grids, and 2 threads performing transformation. And now what's the difference between grid shifting and without grid shifting? So we are going to Atlantic City, and the red one is without, and blue one is with shifting. So the difference is 100. I don't know if can you see these little numbers? It's more or less 100 feet, so it's around 30 meters error if you don't use them. But if you're fine with it, then it will be faster. So again, boost geometry is faster, and this time the difference is bigger, because there are basically the grid shifting code was rewritten, and we are using modern in case of shared grids, we are using modern locking mechanisms like unique lock and shared lock, unlike Proj 4, which I think use simple mutexes, as far as I remember. And in case of boost geometry, you can explicitly don't use grids, which makes it very fast compared to using grids, but you don't get the accuracy. So boost geometry is flexible, fast. It's easy to achieve thread safety, because with Proj 4, with previous versions of Proj 4, it was not possible to be thread safe, because they were using a global error reporting mechanism like this error no system tool. Now it is possible, but you have to create projection context, one per each thread, and use a different function. So additional code. And with boost geometry, because after you create the transformation, it's constant, you can just use it with multiple threads. You don't have to do anything else. Unfortunately, there are less features in boost geometry. So if you need some less common stuff like geogrids or 3D transformations or pipeline operator, then you'd have to use Proj 4. And in boost geometry, there's also no init parameter and no axis parameter. I mean, they're not supported. Because in boost geometry the order of coordinates is defined at compile time, but I think this might be changed, because it maybe would be needed in some cases. But there is no init, because in Proj 4 init you also loads EPSG, for instance, various things from files. And this is something we would like to avoid. Right, and if you're wondering how these pictures were created, with this extension. Thank you.
Thank you. Please us 5 minutes of questions and answers. Shall we sort of get from left to right like this?
Sure.
Do you have any plans to add additional dimensions? I work with robotics, and this geometry is great. I was wondering if, like, robots have many axes and projections that are really important. So,
Right, but for robots,
request?
right.
Many dimensions.
You're talking about, for instance, robot arm, right? And right. So this would probably be different kinds of transformations, right? Which should probably be faster than what I shown. So maybe boost QVM would be for you because they have matrices and quaternions. So maybe something you'd like to use instead. Well, there is in boost there is function called transform where you can pass a matrix defining the transformation and this way transform anything any geometry you like. So this is also what you could use. So either this or QVM, but probably not SRS transformations.
Are there any plans for 3D support?
It's in the future plans. Right. So yeah, we plan to add 3D and actually 4D because there are also additional data which can be passed with points. But it's not there yet. But yeah, we are planning it. Which ellipsoidal transformation methods? Right. Yes, it's under the hood. There is it's the same, basically the same code as Proch 4 because it started as well, not a port, but it was heavily tinkered with, but it was basically Proch 4. And it was started mainly because Proch 4 only used doubles and boost geometry allows to define any coordinate type. But yeah, we are using the same method, and yes, between ellipsoid 2WGS is used or NAD grid, right? Because it depends on datum. So in this rare case of North American datum, grids are used instead of 2WGS. And in some cases, actually I was not entirely honest with you because there is a rare case of 3D representation of coordinates which is Earth-centered, Earth-fixed, which is also supported, but yeah, I'm not talking about that right now because it's a different story. Yeah, so we are using the same method as Proch 4. I don't understand the question entirely.
So I'm coming from using iProJ to be able to call bindings in Python. Is there any command-line interface that you can use to use boost geometry from other?
Oh right, something like CS2CS. You're talking about calling a tool from Linux
Yeah, something you could call on the command line.
command line.
Yeah.
Right. No, there is.
Yourself. You can create that yourself.
There
You
is
can create
no.
a sample script with Adam Show and compile it and then place it in the command line.
It's like one simple of code, I think.
But there is Proch 4 based one. It's called CS2CS with 2 as a number.
Okay, the last question. Yeah, you have the Proch 4 strings and you have your own dynamic inside it and define things. Which boosters do you need to get those?
169 but without with all of the things I showed here compiling without problems 170 which is not there yet. But but most of the things will work.
Let's wrap it up. Thank you very
Okay,
much.
thank you.
Yeah. Thanks to the copies of Lewis